Welcome to our halfway through Unit 3 review. I'm Wes Winter. I am a chemistry streamer here for Fiveable. So without further ado, today, what we're specifically going to be focusing on are what the heck are intermolecular forces, why this relates to the states of matter, and just for funsies, we're going to kind of go into detail with the ideal gas law, do a problem, see how comfortable, familiar you are with those. If we get finished through this any quicker, maybe I can field a question or two that you all have. So of course, make sure to check out Twitter, Instagram, YouTube. They will inform you of all the upcoming streams. So let's go ahead and get started here. Intermolecular forces. Once again, I kind of tasked you with thinking about the different types of solids, liquids, and gases, and also the different types of intermolecular forces. So if you have any questions about those things, once again, I want you to propagate those whenever, and I will flag them. So getting started, intermolecular forces, what the heck are those? So let's look at the word. Let's dissect it a little bit. The prefix inter is referring to between. So when we're looking at an intermolecular force, we're talking about the force of attraction between one molecule and another molecule. Don't forget that when we see the word molecule, we're talking about the smallest subunit of a covalent compound. So this covalent compound can contain anywhere from 1 to 2 atoms to hundreds of atoms. So really kind of identifying what am I dealing with first before we even call it an intermolecular force is important. Ionic compounds don't truly have intermolecular forces. They have what is called intramolecular forces. And if you guys look at our streams from the prior weeks, we talked about ionic and covalent bonds in detail there. So when we're looking at intermolecular forces, once again, we're looking at the force of attraction between molecule A and molecule B. How does this one thing interact with this other thing over here? And the more we know about these intermolecular forces, the more we know about some of those bulk scale properties of those things. That's going to be like melting point, boiling point, viscosity, surface tension, vapor pressure. These 5 are the big ones, but it will absolutely affect some of the other bulk scale properties of those molecules. So kind of keep that on the back of your mind as you're dealing with what are intermolecular forces and why are they important? They are important because they're going to tell us whether or not something can melt at a higher or lower temperature than something else, boil at a higher or lower temperature than something else, have a stronger force of attraction between molecule A and molecule B. So the first one that we're going to be looking at today is not the strongest. It is the dipole-dipole force. The dipole-dipole force is the force of attraction between polar molecules. So first molecule is going to be polar, the second molecule is going to be polar. Remember, polar molecules are molecules that have areas of positive and negative on them. There's a region where it's slightly positively charged and slightly negatively charged. This is due to the electronegativity difference, and due to Coulomb's law, opposite charges attract, okay? So once again, every single polar molecule you will look at has dipole-dipole forces. A molecule is polar if it's non-symmetrical. So what we're going to do in a second here, I'm going to kind of be switching between slides and my online whiteboard. You have to be fairly comfortable with drawing Lewis structures. Quickly drawing Lewis structures will help you identify whether or not a molecule is symmetrical or not. And also I'll help you identify if it's polar. Because the second you say, hey, this molecule is polar, then you know it has dipole-dipole forces between the particles. So what I want to do is this. I'm going to kind of quickly look at some examples of polar molecules. So what we have here is hydrochloric acid or hydrogen chloride. We have H2S, or that's going to be hydrogen sulfide. And then we have CH2O, which is formaldehyde. All of these molecules are polar molecules. And therefore, if you were to draw a HCl molecule compared to another HCl molecule, you'll be able to see that there's going to be an interactive force between them. And once again, we call that a dipole-dipole force. So I'm going to kind of jump onto my whiteboard app in a second. But kind of a silly little image here. Our polar bear has a slightly positive end and a slightly negative end. Okay. So HCl, this is going to be the first one that we're looking at today. Hydrogen chloride is a fairly straightforward molecule to draw, but just as a reminder, we kind of want to think about the number of valence electrons each one of the elements has. Hydrogen has one available electron. Chlorine, while it has a lot of electrons, only 7 are available for bonding. So when we go ahead and look at this molecule, we know that hydrogen is going to form a single bond with chlorine, and chlorine is going to have a bunch of negatively charged electrons surrounding it. These are the valence electrons here. Cool beans. There we go. So there is the Lewis structure for HCl, hydrogen chloride. Just as a super important reminder, I know this might be obvious to some of you, you never draw more than a single bond to hydrogen. You never draw lone pairs around hydrogen. So your molecule will always have single bonds with hydrogen. If it has hydrogen, draw a single bond with hydrogen to something else. All right, let's check this out. So when we're looking at this molecule here, we know that hydrogen has a slightly positive charge and chlorine has a slightly negative charge. Why is this? Well, when we're looking at hydrogen chloride, HCl, chlorine is more electronegative than hydrogen is. So what that does is it allows for the electrons that are in this bond to more highly favor being around chlorine than they do hydrogen. It makes chlorine more just barely negatively charged than hydrogen is. So we draw these delta signs, which just means delta just means partial to represent that. Delta means partial to represent that. And that looks like an S, so I'm just going to kind of connect that there. And it's the lowercase delta. It's not as strong as an ionic charge, so that's why we don't say a full positive or full negative. We just say partially positive or partially negative. But once again, chlorine is going to be negative on that side because of the electrons in the bond, not the lone pairs. So one of the biggest common mistakes that we see with this is that, oh, chlorine has a whole bunch of lone pairs, that makes it negative. No, it's all about the unequal sharing of the electrons in the chemical bond. Now, once again, if you want a more specific definition for polar and nonpolar, look at the older slides or older videos that we have. But today we're talking about intermolecular forces. So how does this molecule attract to another one? So if we are to draw another Lewis structure, which looks just the same with lone pairs around the chlorine, single bond between the chlorine and the hydrogen, we know that chlorine is going to be slightly negative and hydrogen is slightly positive. What do opposite charges do? And I feel like that's the common thing. What do opposite charges do? Opposite charges attract. So we get this negatively charged chlorine attracting to this positively charged hydrogen, and this attractive force here is called a dipole-dipole force. And that's our first force of attraction. This is showing how molecule A is attracting to molecule B. Let's go ahead and move on here. What I'm going to quickly go ahead and do is show you how a H2S molecule can interact with a formaldehyde molecule. So the Lewis structure for H2S looks something along the lines of this. You're going to have a single bond. Remember, it's hydrogen, so you can only have single bonds. And H2S is a bent molecule. So here is our bent H2S. Now, based on these two molecules here, which is more electronegative? Sulfur is just barely more electronegative than hydrogen is, so it will orient itself such that the hydrogens are slightly positive and the sulfur is slightly negative, just like this. So let's go ahead and say we have a mixture. Well, we're just going to kind of get funky here. A mixture between H2S and formaldehyde. Well, formaldehyde has a more electronegative oxygen molecule, and that's going to double bond to the carbon single bonds to each of the hydrogens here, and there's lone pairs on the oxygen just like this. Oxygen is more electronegative than both carbon and hydrogen put together, so it becomes slightly negative and the hydrogens become slightly positive. The way this molecule would orient itself is such that the negative oxygen will come and orient itself near the positive hydrogen of the other molecules. And once again, this here is still called a dipole-dipole force. This is showing how this one molecule here is attracting another molecule over here. Excellent. Alrighty, cool. So we're going to slowly move away from dipole-dipole forces, but before we do, we have a very special type of dipole-dipole force. We're going to switch back to my slides here, nice and big again. Hello. So once again, we're still on our HCl, H2S, and CH2O. All of these, because they're polar molecules, have dipole-dipole forces. So let's go ahead and move on. Second type of intermolecular force, don't forget, force of attraction between two different molecules, is going to be the hydrogen bond. A hydrogen bond is very specific. It's the force of attraction that forms between molecules, that contain hydrogen bonded to fluorine, oxygen, or nitrogen. There's a really awesome, silly, stupid mnemonic. Hydrogen bonding is fun. Hydrogen bonding is fun. It's not really fun. It's fun. Yeah, it's a good time. Hydrogen bonding is a good time, right? But this mnemonic, what does it tell us? It's showing us that the only way you can have hydrogen bonding is if hydrogen is directly bonded to F, O, or N, fluorine, oxygen, or nitrogen. And if it's not the case, then it's not a hydrogen bond. Really quickly, I do want to remind everyone that hydrogen bonding is the strongest type of intermolecular force if you're asked to predict it. And I'll tell you what I mean by that in a second. It is definitely stronger than dipole-dipole forces and London dispersion forces as well. But it is, of course, not a true chemical bond. So I want you to keep that on the back of your mind. It is not a chemical bond, but it is a very strong type of intermolecular force. And what is cool about this is it does affect the structure of biomolecules. By biomolecules, I'm usually referring to nucleotides or amino acids. And it's what allows for things like our DNA to have that double helix structure. One strand of that molecule will attract to another strand of the molecule based only and solely on hydrogen bonds between the adenines and the thymines, there we go, and the cytosines and the guanines. Amino acids will arrange themselves in different ways to orient themselves and make specific DNA structures based on the hydrogen bonds. That's how we go ahead and get our secondary structures. And in case you're also doing AP Bio, or you remember that from AP Bio last year. So let's go ahead and look. Let's go ahead and look at hydrogen fluoride and methanol. Now, I do want to point out in both of these molecules, they have the hydrogen bonding as their strongest intermolecular force. Hydrogen in both of these molecules is specifically bonded to an F, O, or N. So what we're going to do here is we're going to go ahead and look at hydrogen fluoride, which the Lewis structure, by the way, looks just like hydrogen chlorides. The only difference is instead of chlorine, you have the fluorine here. And when we go ahead and draw the Lewis structure for this, it shows us that fluorine, being the most electronegative element on the periodic table, it still is partially negative compared to that of hydrogen, meaning that hydrogen is the positive end of the molecule and fluorine's the negative end. We can go ahead and do this again because this being intermolecular forces, we need to show how one molecule attracts another one. We have HF, HF, this side being slightly positive, the other being slightly negative. We have our attractive forces between the oppositely charged things, and wouldn't you know it, is this a dipole-dipole force? Is it? I don't know. No, I totally know. It is. It is still a type of dipole-dipole force, but the main difference is that it is a very strong dipole-dipole force, and the strong dipole force is called a hydrogen bond. It's just a strong type of dipole-dipole force, and it only arises when we have hydrogen directly attached to the fluorine. So some of you are probably looking up at the formaldehyde molecule that I drew here, and this is still considered a dipole-dipole force and not a hydrogen bond because the hydrogen is not directly bonded to the oxygen. So what I decided to do is add a molecule here to kind of show you. So that's going to be our formaldehyde, our methanol. The Lewis structure for methanol has 3 hydrogens bonded to carbon. The last one is single bonded to an oxygen, which is then bonded to the hydrogen. Because you have the hydrogen directly bonded to the oxygen, that makes this hydrogen very partially positive and this oxygen very partially negative. and this end of the molecule can interact with other methanol molecules in a very specific and close way. Awesome. So those are our hydrogen bonds. Our last type is, of course, London dispersion forces. So London dispersion forces are considered to be the weakest type of intermolecular force. And once again, that's going to be specifically when you're asked to predict the relative strengths of these molecules. I will get to, once again, the concept or idea that I'm asking about in a little bit here. London dispersion forces are the forces of attraction between nonpolar molecules or atoms. So this is also going to be true for our noble gases. Noble gases absolutely have intermolecular forces. They are just going to be called London dispersion forces, though. Our London dispersion forces arise due to the random motion of electrons. Electrons are these like little negatively charged balls right there flying around the atom. And if they just so happen to be on one side of the molecule, it makes that molecule slightly negative on one side and slightly positive on the other. Because of that, that molecule has a dipole moment. Now, this dipole moment is exactly that. It's just a moment. It doesn't last. It's fleeting. And because of this, the London dispersion forces aren't very strong. With that being said, okay, they can still be very strong. The reason this is that the more electrons it has, the more polarizable the molecule is. And polarizable is a good word for you to kind of have on the back of your mind. When something is more polarizable, it has stronger intermolecular forces. And what I want you to think about is this now, because we're going to slowly start transitioning into the states of matter. If we are considering water is a fairly small molecule with really strong hydrogen bonds between molecules and molecules. At room temperature, water is a liquid. If we consider wax is a very large molecule. It contains upwards of 20 to 30 carbon atoms, is a solid at room temperature, and all it has is London dispersion forces. What this says is that the London dispersion forces in wax are supposedly stronger than the hydrogen bonds in water. And the evidence is that wax is a solid at room temperature while water is a liquid. Now, the reason that is all because of that last statement that I went ahead and said. The more electrons, the more polarizable. Wax has a ton of electrons, and it also being a long chain carbon, the molecules tend to like interact and intertwined with each other, making it hard for them to break apart. This causes for them to totally, absolutely be solid at room temperature, and therefore have stronger forces of attraction between them. Water molecules, being incredibly small, are not as polarizable, even though they're very polar, and that's why they're liquid at room temperature. All right, so with that being said, we are slowly going to transition into states of matter. What I want you to do is list your favorite state of matter in the comment section. Favorite state of matter. I'm going to list mine. I'm over here in Santa Cruz, so of course my favorite state of matter is solids. Bodhi likes plasma. While plasma is a great type of intermolecular, state of matter, we are really only going to be focusing on solids, liquids, and gases. I'm sorry to say. All right, cool. So let's go ahead and sorry. Let's go ahead and move on here. So the three states of matter, as we know, are the solids, liquids, and gases. So what I just kind of quickly wanted to make sure everyone was comfortable with was the idea of the particles within each one of these substances and how they interact with other particles. The main difference between solids and liquids is flow. The only difference between, in my opinion, a liquid substance and a solid substance is the ability for two particles in liquids to switch places with each other, and solids don't have that ability. They're in a rigid position. That doesn't mean they're not moving. Remember, in solids, in the kinetic molecular theory, it states that we have some vibrational and rotational feelings within those particles, but they do not move their position. They do not have the ability to, once again, flow. Flow is the nice word that we like to use. Liquids are still right next to each other. They have strong enough intermolecular forces to keep the particles touching, but not strong enough intermolecular forces to keep the particles from not flowing. Last but not least, we have the gases. Gases, when we kind of get into our kinetic molecular theory statements, are mind-blowing. They are totally crazy. They have really ridiculous properties, but the way I like to think of it is one gas particle is here, the other gas particle is not here, not here. It's further and further and further and further and further. I'm gonna have to leave the room. I'll be right back. No, the idea is, right, that the gas particles are almost infinitely far apart compared to how small the particles actually are to each other. So once again, solids, liquids, particles right next to each other. Solids have that vibration, they're right next to each other. Liquids have the ability to flow past one another, but they're still right next to each other. Gases, infinitely far apart, bouncing off of each other, and bouncing off the walls of their container, et cetera, et cetera, et cetera. So let's start with liquids, mostly because this is the one that's mostly related to the intermolecular forces. Knowing this chart on the back of your head, back of your hand, knowing it well is going to do you so many favors, because honestly, they're going to ask you a question related to one of these 5 things in terms of the properties of liquids. Liquids. So, man, even when I'm pretty much by myself, I make bad jokes. So first off, boiling point. Boiling point actually relates to vapor pressure. Vapor pressure refers to the pressure of a gas that's at equilibrium with its liquid phase. And boiling point is the temperature where the vapor pressure of a liquid equals the atmospheric pressure. So actually, depending on temperature, where you're at on planet Earth, the boiling point of a substance can actually change. You probably are all pretty comfortable with the boiling point of water being 100 degrees Celsius. That's actually only true at sea level if it's 1 atmospheric pressure. What do you know? Melting point is going to be the temperature where a solid and liquid substance exist in equilibrium. Now, this is the second time the word equilibrium has come up. Equilibrium refers to a dynamic process where particles are converting from one phase to the other at the same rate that the other converts back. So what I mean by that is a solid will melt into a liquid particle. A solid particle will melt into a liquid particle. At the exact same time, some other liquid particle is refreezing into the solid state. Let's talk about this in terms of vapor pressure. A gas particle will condense into the liquid phase. At the same time, another liquid particle evaporates into the gas phase. These are equilibrium processes, and they're dynamic. Once again, it's when the rate of one is exactly equal the rate of the opposite process. So you'll have the 25 particles evaporate at the same time that 25 particles condense. Viscosity and surface tension are really just kind of good words to have on the back of your mind. Viscosity is referring to the resistance to flow, and surface tension is referring specifically to the resistance in an increase in surface area. So let's talk about viscosity first. I really like to think of viscosity as like oozing, moving slowly. The word viscous is kind of viscous. It's really slow. Examples of viscous materials are going to be molasses, tar, maple syrup. And especially when we're thinking about molasses and maple syrup, I like to think that those things make sense. Molasses and maple syrup are essentially sugar. They're essentially sugar. Sugar, being a large molecule, also has 6 different places to have hydrogen bonds. So that means it has really strong intermolecular forces with other sugar molecules. So when they come into contact with each other, they're still in the liquid phase. They still have enough energy to flow past one another, but they do so at such a slow rate. That's what makes them viscous. And it's because the hydrogen bonds on this molecule are attracted to the ones on this molecule, making it flow really slowly. And then surface tension, the way I kind of like to think about it, this is, by the way, absolutely the definition you want to use, but the way that I like to think about surface tension is it's referring to the ability to break through a surface. So for example, water has really strong surface tension. That's why things like bugs or spiders or leaves can actually float on top of the surface, because the weight or the mass of the spider, the bug, the leaf is not strong enough to break the individual intermolecular forces. Internalize this graph. I've given you the slides, so you can definitely use these for your own good later. Solids. So once again, solids. There are 5 different types of solids. We have metallic, ionic, network covalent, molecular solid, and atomic solids. Once again, knowing and just kind of internalizing this graph will be super useful for you. Metallic substances have the ability to conduct electricity and heat. They are malleable, which just refers to their ability to be hammered into sheets. They are ductile, which refers to their ability to be pulled into wires. And they're lustrous. They're shiny. And this is all due to the sea of electrons model. These models were talked about in some of our older streams, but if you have questions at the end, I can definitely go over that. Ionic substances are hard, brittle, they have very high melting points. They are mostly water soluble. We'll talk about solubility in the next stream. And they are also considered to be electrolytes. Remember, electrolytes are substances that conduct electricity when they're dissolved in water. Network covalent molecules are awesome. If any of you happen to own a diamond at home, which some of you actually might, that diamond, that single diamond, is considered to be a single molecule. It's literally one carbon molecule atom bonded to another carbon atom, bonded to another carbon atom, bonded to another carbon atom, carbon atom, carbon atom, carbon atom, like all every single which way. So if you were able to hold up a diamond, you're holding one molecule, which you can't really do that with anything else. Network covalent compounds and molecules and solids are amazing, in my opinion. They are incredibly hard, and diamonds don't really have a melting point, because in terms of a network covalent compound, you would actually have to break the bonds between carbons in order for them to move past one another. Remember, melting in the world of chemistry, boiling in the world of chemistry, you're not really referring to breaking chemical bonds unless you are a network covalent or an ionic substance. Otherwise, you're breaking intermolecular forces. Molecular solids are held together by intermolecular forces and therefore have relatively low melting points. You can think of molecular solids as like ice, liquid water being solid water, dry ice, carbon dioxide, or even beeswax like I referred to earlier. These are all examples of molecular solids. And then last but not least, atomic solids. These are held pretty much together by London dispersion forces and London dispersion forces alone. They have extremely low melting points, but some of the London dispersion forces, once again, can be extremely strong. For example, iodine. Iodine is a solid at room temperature. And the reason that is because it has a lot of electrons, making it more polarizable. All right, last but not least, gases. So I feel like a good spot to start with the gases is specifically referring to the kinetic molecular theory. Now, as an overarching idea, the kinetic molecular theory says that particles are always in motion. Particles are always in motion. So the first statement says particles are in constant rapid random motion. I think that makes sense, seeing as just for the kinetic molecular theory, particles are in motion. Statement 2, gas particles are small compared to the huge distances between them. This is referring to literally there being a almost infinite distance between particles, and this also refers to the fact that particles are volumeless. Statement 3, there are no forces of repulsion or attraction between particles. Statement 4, collisions between gas particles are elastic. An elastic collision just refers to there being no net loss of energy, specifically kinetic energy. So if you have one particle moving in and another, it will completely transfer its energy to that particle. Or if a particle bounces into a wall, it bounces off the wall with the same speed it came in with. And the last statement is this. Last statement says that the average kinetic energy of particles and the temperature are directly related to each other. This allows for us to understand more about the velocity of particles And you want to basically relate the velocity to two things: the temperature of the solution of gases that you have, or the mixture of gases, or the sample of gases that you have, and the mass of the particles within them. Faster particles are usually lighter and at higher temperatures. Slower particles are heavier and at lower temperatures. Internalize that and kind of keep that in the back of your mind. I'm wondering if any of these statements are weird to you all. Think about this again. Particles are infinitely far from each other. They have no volume. There are no forces of repulsion or attraction between particles. The collisions between particles are elastic. This is weird because these statements are not true for anything. What I need you to kind of understand and think about this is that ideal gases follow all these rules. And this is kind of my favorite part. Ideal gases don't exist. There's no such thing as an ideal gas. But what we do is we kind of model the behavior of gases, real gases, off of this ideal perfect situation, where once again, particles are volumeless, even though they're not. They're very close to it, though. They are infinitely far apart. They're not. They're very close to it, though. The collisions are elastic. They're technically not, but we're going to say that they are. And last but not least, particles have no forces of attraction between each other. That's absolutely not true. The first half hour of this section has been talking about intermolecular forces and how one particle attracts to another. It's just that. Particle A and particle B in a gaseous mixture have so much kinetic energy that one comes flying by the other. And did you see it? Their force of attraction, they're like, hey, I'm attracted to you. And I was like, nah. And that's it. So the idea that I kind of want you to take away from this is that real gases behave more or less ideally. It's just that real gases behave more ideally at very high temperatures and very low pressures. And these statements kind of help us identify, they help us identify that, hey, yeah, low pressures means there's almost an infinite distance between particles. And then at higher temperatures, they have a huge amount of kinetic energy, so they were able to transfer their energy between them, okay? And last but not least, real gases tend to be small and nonpolar. Helium is considered to be the most ideal gas on the periodic table, and it behaves the most ideally. But even so, remember, it behaves even more ideal at higher temperatures and lower pressures. So, of course, what am I leading to? The ideal gas law. The ideal gas law is PV equals nRT. It's relating 4 of these variables to each other. And if you know 3 of them, you will always be able to identify the 4th of them. P is pressure. Remember, pressure in the physics world is a force acting over an area, but really your takeaway should be that gas particles exert pressure by colliding with the walls of their container. When they hit the walls of their container, they are exerting pressure. You're under some pressure right now from the atmosphere. You're under 1 atmospheric pressure. V stands for volume. It should always be measured in liters. It's just referring to the size of the container because remember, gases occupy whatever container they're in. So whatever container you have, that is going to be the volume in liters. N is moles. Moles is referring specifically to the number of particles. I wanted to relate quickly that as the number of moles increases, the number of particles in a sample also increases. So this will do things like increase collisions, which therefore would increase the pressure. Last but not least, temperature. Temperature is always measured in Kelvin. Remember, if you add 273 to the Celsius temperature, you will get Kelvin. As temperature increases, one last time, so does the particle speed. So based off of these 4 things, we need one last one, and that's going to be R, the universal gas constant. And this is going to be where I switch back over to the whiteboard one last time today. What we're going to do is check out this problem. And if you feel like you're pretty comfortable with the ideal gas law, I want you to try it on your own. But the ideal gas law is, this problem, I think, really nicely kind of shows how to use, the ideal gas law. What is the volume of 95.5 grams of helium at a very high temperature, 884 degrees Celsius, and a pressure of 0.831 atmospheres? Now, 831 is still relatively high in the world of pressure, but like I said, helium is probably one of the more ideal gases, so we're going to go ahead and check that out. So let's go ahead and switch over and see what we can do with this. So we have a few pieces of information from this. The information that we have, it seems to me, is the mass. And the mass of our helium sample is 95.5 grams. So this is going to be our mass. Our temperature is going to be 884 degrees Celsius. And last but not least, it looks like the pressure is given to us in atmosphere, which is going to be 0.831 atm. Before we do any work with this, we need to actually convert so that we have the right things, because we're looking at PV equals nRT, right? So pressure needs to be in atmospheres. Hey, that's actually good. Volume is what we're looking for. N, remember, is the weird one. It's referring to moles. Looks like we have grams here, so we're going to have to do some conversions with that. R is the universal gas constant, which will always be 0.0821. R is 0.0821 atm liter per mole Kelvin. What's really nice about this is that this value will always be given to you on your AP chemistry test sheets. And this also tells you what units you need. So notice you have the atm units, your liter units, your mole units, and your Kelvin units. All right, so let's go ahead and get to work here. We need to convert mass into moles. Remember, the easiest way to do that, and probably the only way to do that, is by using molar mass. The molar mass of helium is essentially 4 grams for every 1 mole. 95.5 divided by 4 ends up being 23.9 mole of helium. I started with 3 significant figures and I ended with 3 significant figures. Remember, in order to convert between Celsius and Kelvin, I add 273 to my Celsius value. So 884 plus 273 gets us 1,157 Kelvin. Once again, our ATM, our pressure, is in the right unit, and our R is as well. So what we're going to go ahead and do is this. We're going to take and plug all of our values. So we have mole. We got that from the mass, just using molar mass. We're going to plug that into N. We have our temperature. We're going to take that and plug that into our temperature here. Looks like we have our R value here. It's going to go whoop, little switcheroo. And then last but not least, the pressure. And that's going to be right here on the right-hand side. So we end up getting, let's scoot down here a little bit. We end up with 0.831 times V is equal to 23.9 times the R value, which is 0.0821, times our temperature in Kelvin, which is 1,157. Divide the pressure over 831. 831. And I'm kind of curious, did anyone actually end up getting this before I finished? If you did, great. If you didn't, that's fine too. I'll give you a second to answer if you feel like you have it. Finish up here in 5, 4, 3. See, anyone gonna beat the gun here? 2, 1, and that's right. The answer is 2,700 liters. We have a winner, 2,700 liters. I ended up choosing 2 significant figures. Actually, I don't know why I chose 2 significant figures. It should have been 3. I am so sorry about that. So let's quickly do it one more time. 23.9 times 0.0821 times 1,157. 1,157 divided by 0.831 gets us 2,730. So we'll just quickly change that so we have the right answer here, 30 liters. And there we go. So it's a massive volume. In order to have a helium sample with this volume pressure, pressure, moles, etc., etc., etc. Awesome. That's our first half of Unit 3. Unit 3 is kind of a crazy one. There is, once again, lots of stuff referring to intermolecular forces, the London dispersion forces, dipole-dipole forces, hydrogen bonding. We have different properties of liquids and how that relates to the intermolecular forces. We also, of course, have the properties of solids and different types of solids. And we quickly just kind of related to the intermolecular forces to the kinetic molecular theory and the ideal gases. Please, I'll stay on for like 60 seconds here. Let me know if you have any questions relating to these things or other things in the world of chemistry. I'd be more than happy to answer them for like a couple minutes. Could you do kinetic molecular theory? Yeah, so I can go back really quickly to the slides for gases, or can you give me a little bit more specific as far as like what you're looking for with the kinetic molecular theory? So up here, what I've listed is the kinetic molecular theory for gases. Just as a whole, kinetic molecular theory is this idea, this statement that molecules are in constant motion. If you have a solid substance, the particles are vibrating in place, they're still moving. If you have a liquid, the liquid particles are right next to each other, but flowing past one another. And then gases are zooming around, bouncing off of each other, bouncing off you and me, bouncing off the containers, the walls of their container. Specifically, these statements for the gases, 1 through 5, are never going to be asked in this order. Literally every textbook, every website, every video I've ever watched has these listed in different orders. Sometimes they're combined, et cetera, et cetera, et cetera. So you're never going to see a question that says, what does the kinetic molecular theory for gases first statement say? No, what a question you might see is something along the lines of, why can we not consider gas particles to be infinitely small? Or are there forces of attraction or repulsion between particles? That's kind of what you would be looking for with that. But yeah, I don't know if I've answered your question. Is that kind of what you were looking for? Or are you looking for, awesome, yeah. So once again, if you look down below, there's a little link that says slides. You can go ahead and click on that and check out the slides for yourself. One other thing that might come up, and that since I have some time, I'll do this. Let me go ahead and share with you guys my whiteboard for one last thing here. One thing that we can relate the kinetic molecular theory to is something called the Maxwell-Boltzmann Distribution. The Maxwell-Boltzmann Distribution is a graph showing the relative velocity or kinetic energy of particles. So this will be velocity, we'll just say. And down below, no, sorry, that's wrong. Velocity will be the x-axis. And the number of particles will be the y-axis. Because we have particles always moving at different speeds, each one of these graphs will always be represented like this, where you have a high peak and then it kind of ends up trailing off to the side here. You need to know how this graph changes for different substances. So one of two things can happen. It can either move further out to the right because of temperature or because of the mass of the particles. So each one of these can be the same substance. Each one of these can be the same substance or a different substance with different masses. So notice, first off, the peak's height changes, but the distance, the average velocity increases as you go from black to red to blue. Two things can do that. Heavier particles move slower, so heavier particles will be represented by the black line. And also at low temperatures will be represented by the black line. And that black line is basically just saying you have a larger amount of particles that are moving more slowly. And once again, that's true for both of these statements, for large particles or particles that are moving at lower temperatures. The blue line represents lighter particles. or higher temperatures. Higher temperatures, higher particles. And that's basically showing us that a majority of the particles are moving faster. And once again, this is true for both. This is true for both light particles or particles at higher temperatures. Cool. All right, y'all. Have a great week. Good luck with chemistry. Fiveables got your back. See you all soon.